Hello boys and girls, welcome to another episode on our YouTube channel. My name is Craig. I'll be your host in this vlog where I discuss and drink beer and do something with electronics. In part 1 of this series we looked at the MC33063 IC and we used it as a buck regulator. Today we're going to look briefly at a boost regulator and we're going to see if we can combine the two to make a buck boost regulator. A little bit of theory, I'll get on the bench and go through it quickly, and then we'll breadboard the circuit and see what we see on the scope. So in part 1 of the series we actually looked at the two devices, this inductor and this capacitor is a storage device, and we said that the capacitor is a electrical storage device, whereas the inductor is a electromagnetic storage device. And for those of you wondering, I'm drinking a Lion Lager today, AB InBev, SAB AB InBev beer. I quite like it. It's one of my go-to beers. It's not too high in alcohol, 4%. Original recipe apparently from what it was when they discontinued it about 20 years ago. Anyway, let's not get too sidetracked on the beer. So we said with our buck regulator, if we put a switch here and we could control the frequency, we'd have a current flowing through the inductor. The inductor would build up a magnetic field to store the energy. It would charge up the capacitor. The capacitor will keep our voltage constant. But when we switch off the switch, the inductor doesn't like a change in current flow, so it will keep it flowing there in that direction. Capacitor will discharge, and if we had a sensing circuit we could switch this on and off to our heart's content, so we could bring this voltage amplitude down. We could buck the circuit. Now we have another circuit very similar, we call it a boost circuit, and a boost circuit is very simply put, same thing. We go through our inductor, we have a diode, we'll call that our output, a capacitor, let's make that electrolytic, and we put the switch here. Now this is a boost circuit. It looks very similar. What I want you to note, we'll call this VCC, we'll call this V out. Notice we have nothing disconnecting our power supply or our supply voltage. So the supply voltage is going to go through that inductor in a default state, overcome that diode, we'll have a voltage drop or whatever the diode is, charge up the capacitor and go out. When we create or we close that switch, the current is going to go like this. We now have a dead short. That means we're going to build up a bigger magnetic field, stronger. We open the switch, current doesn't change direction, it's still enough to jump that plus the supply, charge up the capacitor, and we can get a bigger magnitude voltage on the output based on how often we are switching this switch. So that is our typical boost circuit. Now what happens if we combine this? Let's say we put that switch after the inductor plus our diode before there, or we've created a buck boost. Well, in theory anyway. Now the chip we're using is not ideal for this. If we remember, let's come back to our MC33063. It tells us it can be used for buck, boost or inverting switching regulator circuit, so either or. But I have a suspicion, and I've designed something and we're going to see if it works, that we can use this chip as a buck boost. So what I'm going to do, I'm going to get the circuit out, and then what we'll do is we will keep this block diagram as a reference so we can see what's happening in our in the circuit that we've designed. So let me get our circuit out and then we can discuss it further. And so here we go. I'm just going to zoom in a little bit. Here's our circuit that we've designed. Similar to what we did in the buck circuit. All I've said is we're going to have our batteries or solar cells in parallel this time, so we'll have our 6 volts in parallel, so we can get a higher power. We can double the current output, or we can have our PP9, again each one with a blocking diode. The capacitor, my calculation said 100 mic. I'm going to just go a bit bigger with 470 U's because 470 micros, because that's what I had on the desk. This time we're going to put in a 15 milliamp current sense resistor. And again, if you read this data sheet, it is very confusing, because what they don't tell you is this 15 milliohm or this current sense resistor is actually limiting the current on, for want of a better word, the primary side, the upstream side, the current that this thing will switch, not what is downstream. Very important. If we have our MC33063 that's going to do our switching. What you notice is I've put in 2 MOSFETs here. If you remember from the first series, and I'll put a link into the first series, and I'll also put a link to the circuit in the description below, and at the end of the video there will be a link to the first video in the series. If we look here, SWC, SWE, we had a thing called saturation voltage across that transistor that's inside there, and that saturation voltage is 1 volt. And I also said in the first video, the bigger the sum of the saturation voltages or losses, the more inefficient our circuit is. So I've used MOSFETs to basically bypass that switch in there. I've used the P-channel MOSFET here, 9640N, and I've used its complementary N-channel 640 IFR from Infineon. Why I've used these MOSFETs is because I had them to hand. So if you're going to design your circuit around this, you're going to have to do a few calculations. For the P-channel MOSFET, what is interesting, our RDS on is 0.5 ohm. So if I took our 0.5 ohm, in other words, this MOSFET is now running flat out, maximum current pass through, or in our case, our current pass through. It has an RDS on of 0.5 ohm. We're going to pass 0.5 amps. 0.5 ohm times 0.5 amps gives us 250 millivolts. Our VSAT by default across that switch in there was 1 volt. So you see we've gained 750 millivolts. So it's 750 millivolts times the current flow, less energy or heat that I'm going to be dissipating in that MOSFET. P-channel MOSFET has a much higher RDS on than the N-channel. Our N-channel only has an RDS on of 150 milliohm. So the N channels are typically much more efficient. Also, what you must notice, let's see if we zoom in a little bit up here. I can't. There's a little body diode across the top there, a little body diode across the top there. You must be careful with these body diodes. If you put it the wrong way around, obviously your MOSFET's not going to work and you're just going to create a dead short. Not ideal. So if we look at the circuit and we look at our hand-drawn circuits, what have we done? Well, we had that circuit, right? And we still have that circuit. So that P-channel MOSFET is going to pass it through our inductor. Great. Then the second part of the circuit, where we put the switch from the inductor, the rectifying diode and capacitor, well, here's the second part of that circuit. It comes through that N-channel MOSFET. There's its rectifying diode. Again, on the output, I calculated 300 and something micro. I had 470, so I just put 470 in. What do these two transistors do? Or MOSFETs, they're not transistors, they're a family of the transistor. What is important to understand, we have a 10k pull-up resistor there, so our VCC through our current sense, through that resistor, a MOSFET gate does not use current, it uses voltage to switch it. So to all intents, there's no current flowing here. Well, there is, but we're going to just deal with the ideal model. That voltage there will be the same voltage here. So the voltage between gate and source, GNS, gate, source, drain, will be the same. So P-channel MOSFET, the voltage there is the same as that. That MOSFET will be off. Okay. To switch it on, I need to pull that voltage down. If I pull that voltage down, in our case, these two MOSFETs work between 2 and 4 volts, but if I pull this voltage 2 volts lower than that volt, 2 to 4 volts lower than that source voltage, this thing will switch on. Important to note, when you go and read in the data sheet, they'll give you with a P-channel MOSFET, same with the PNP type transistor or something like that, they will give you this value as a negative value. In other words, this must be down on that by whatever they're specifying. So to switch this on, let's come here to our little block diagram. We'll just move it across like this. So to switch that gate on, what I want you to see is the gate is going to pin number 8 DC, the drive collector. The drive collector goes to the collector, then the emitter to switch on the base of that transmitter, which will switch our switch collector circuit on. We'll come back to 1 and 2 just now. That base of that transmitter is switched on by that latch, which comes from this oscillator, the current sense, the current sense or I-peak, current peak limiter, plus the comparator. We'll switch that thing on. So basically we're pulling the gate through to pin 8, so the gate is coming here through there to switch on that switch collector, which is switching on a switch between 1 and 2. And if we come here, we look at 1 and 2, well, what is on 1? We follow it back, it comes after the inductor. Can you see that? Comes to pin 1, comes out pin 2, switches on the gate of this transistor. Now this MOSFET, is important to know, is N channel. It works the opposite of this one. To switch it on, I need to apply voltage, and in our case, again, now this will be the positive voltage. The gate must be 2 volts or more higher than that MOSFET to switch it on. Now you'll see in the data sheet, it will always give you a range. There's 3 states to this MOSFET, and we must think of it like a transistor. It can be off, it can be in the amplifying region where it's amplifying or modulating the signal, or it could be in the fully on or saturated state. So our MOSFET works similar to that. It's either off, it's in what we call a triode state, so it's not saturated, or it's fully on. When it's fully on, we get the best RDS on, we get the best resistance value. So if you're going to use a MOSFET as a switch, make sure you pay attention to what they call the gate source threshold voltage. In our case, for this N-channel MOSFET, we need 2 to 4 volts. The P-channel MOSFET, we need -2 to -4. So in other words, that must be 2 to 4 volts lower than the source. In this case, it must be 2 to 4 volts higher than the source. So what is going to happen? Well, in the dead state, that transistor will be off because the voltage has got nowhere to go. Those switches are off. The voltage at the gate will be the same as the source. That means this transmitter won't conduct. This chip will wake up with its oscillator and everything and say, please switch on. It will pull that gate voltage down because now we've created a short. By doing that, we will drop the voltage on the gate to the source. The transistor will conduct. That current will flow through. It will build a magnetic field. But at the same time as switching that transistor on, we switched the second transistor pair on. So from our Darlington pair, because we switched that transistor on, our gate coming through, we've pulled in there to switch that transistor on. So at the same time that we've pulled that gate voltage down to switch the transistor on, we have now switched this transistor on. We've created our dead short through the output, through the transistor to ground. We build a better magnetic field, stronger flux in the inductor. This thing will come to switch off based on our voltage divider circuit, which we'll get to. The current needs to keep flowing. It will jump the diode, charge the capacitor. We get our feedback here between R5 and R6. Now you see this time I've gone 3K6, 1K. We want 5.75 volts on the output. If you do the maths, 5.75 divided by the 4,600 times the 1,000, you'll see we'll get our 1.25 volts. Reference on VFB. So this will switch and switch and switch. We've got our filtering storage capacitor on the output. I've gone with 470 because I didn't have anything else. I've just put a resistor LED circuit in so that we know if it's on. I've put a blocking diode in here, 1N5819, because we're going to supposedly charge a battery. Well, if the circuit for whatever reason is not working, we want to block whatever's coming back here. This is just a USB connector. I don't actually have one. I just drew it in for the completeness of the circuit. You'll see between D plus and D minus of the USB, I've connected a 200 ohm resistor to terminate it. If you look at the USB specifications and you go back, typically a USB charger has some intelligence in it. Well, it's supposed to. So the device that you plug it in will talk to your charging circuit via this D plus D minus and say, okay, what are you and how much power can you give me, in the simplistic way of looking at it. This would have some intelligent chip that would talk back and say, okay, I can give you 250 milliamps, 500 milliamps, 1.5 amp, 2 amp, 2.5 amp, or whatever. Well, I'm not putting a chip in for this. According to the USB, I think it was 2 specification, if we put in a terminating resistor between data plus and data minus of less than 220 ohms, then this becomes recognized as a DCP or dedicated charging port. So our smartphone, whatever, will come to it and say, hey, what are you? Oh, I see this termination across here. Okay, you're a dedicated charging port. You can give me 500 milliamps. Thank you. And off you go. So the circuit is not that complex. I will put the marked up circuit in the link to it in the description below. Again, we have some alternate circuits up here. If your timing circuit, if your capacitance that you require is over 2 nanofarad, then you should use something like this. It's called a ratio extender. Basically, it allows us to use bigger capacitances, because if you look at the way the chip works, the higher the capacitance, the lower the frequency that I want. So the higher the frequency I want, the smaller CT is going to be, or that the timing capacitor based on load and what we're trying to do. Again, optional output filter, and our snubber network. Remember in part 1, if you haven't seen it, there were huge spikes across the switching device, in other words across there, which is basically across our transistors, or basically from there to there in this case, and there to there. I'm using MOSFETs now. So also what is important to understand about a MOSFET, the gate has a bit of capacitance, right? The drain and the source have capacitance. So I suspect when we measure this on the scope, I'm not going to see that huge ringing. I'm not going to see such huge amplitudes. The reason we put this in is to keep those peaks from destroying our switch. So because of the MOSFET property, I'm not expecting to see huge transient noise here or ripple. The second thing, because we're using MOSFETs, I'm expecting to see a cleaner output here. So that circuit I don't think will be necessary. The ratio extender, well, we're using 680p for our timing capacitor. So we're well below the 2 nanofarads. I don't think we need that. So what I'm going to do, I'm going to breadboard the thing, get it out, and we'll go through the circuit quickly. Right, so there we have our breadboarded circuit. Down there, our MC33063 our little IC. Over here we have our 680 puff timing capacitor. Over there, up here, our input 470 mic input filtering capacitor. We have some, you can't really see it, but just maybe the end of it there. Let's move that out the way. Let's do it like that. That little silver bar is our 15 milliamp current sense resistor. Here's our P channel MOSFET. We have our little freewheeling diode, our inductor. This side, our output diode to rectify. Then we have another 470 microfarad bulk storage capacitor. We have our resistor divider network to go back to there for our voltage feedback. Our little LED with its resistor, and then we have another rectifying diode, blocking diode. Remember we said we're going to go out to our USB, and there's our 200 ohm terminating resistor for our to tell our smartphone device that it is a dedicated charging port. This is just a load resistor. I will connect that into ground as we need it on the scope. Not important. Up there, that's just our voltage pull-up resistor and our feedback or biasing resistor for the transistor base in there. Sorry, you couldn't see it, for the transistor base in there. That little 220 ohm resistor and the 10k pull-up. Those two up there. Other than that, there's not really much to the circuit. So what I'm going to do, I'm going to hook up the scope to it, and we're going to have a look at it. So let's just come out here and I'll show you where I'm going to hook the scope up to. So channel 1, the yellow lead, I'm going to hook up to that point there. Channel 2, our blue lead, I'm going to hook up to that point there, so we'll have it on the gate. Channel 1 on the gate of the P channel MOSFET, we'll have channel 2 on the gate of the N channel MOSFET, and what we'll do is at that point there, our output of that blocking diode, we will put the channel 3 or the pink magenta probe, so that we can have a look at what this circuit is doing. We'll run it at first with no load, minimal load, just the LED and its resistor, so we won't have that load resistor in, and then we'll run it off the bench power supply. Then we'll run it through the same thing, see how it performs with the load, and then we can take it from there. So we get everything hooked up, and then we can take a look at the scope and the power supply. Right, here we are again. We have everything hooked up again. Our yellow probe, we said, is to the gate of the P channel MOSFET. The blue will be to the gate of the N channel MOSFET. The pink magenta will be on the output. We can see our output voltage is 200 and something. So our power supply is off. I'm just going to swing over to the power supply. You've seen this, you're familiar with it. It's off, it's set to 0. I'm going to switch the power on. You can see we're putting in 0 volt, pulling 0 amp, 0 watt. I will turn the voltage up in 1 volt in increments like this, and we'll see what is happening on the scope. So let me just focus more down here. That looks a bit better, you've got more. Right, so I'm going to turn it up in 1 volt increments. So there we go, 1 volt, 2 volts. We just adjust our trigger down here. You can see it's trying to start up. You see what's happening on our P channel MOSFET. Remember I said when we pull the gate voltage low, it's switching on. N channel MOSFET, when we switch it high, then we're switching it on. So it's not doing anything yet. Our LED is not on. We've got 2 volts, 3 volts, 4 volts. Our LED has just come on. 3 volts with just under 1 volt. As soon as we get to 4 volts, we are now pulling or outputting. How much is that? 3.46 volts. So not quite the 5 volts that we needed. So 4 volts, and it's got a 5 volts. 4.6 close, not quite. For your interest, we are pulling 0.018 or 18 milliamps. We'll go to 6 volts. You can see our output voltage is now where we wanted, 5.5. Let's just adjust my trigger up here. Okay, we can sort of get an idea what this device is doing. We're going to go up 7 volts. We'll set my voltage down here, 2 volts. Let's go to 2 volts. There you get a good idea what the buck boost is doing. It's just changed channel 2's voltage amplitude as well. We'll leave it at 1 volt for now. So remember I told you, okay, remember there's not much load on this thing. It's only the LED. Our P channel MOSFET is at, in the off state because the gate voltage is high. The device, the MC33063, pulls that voltage down. At the same time, remember it went through to bias the gate of the Darlington pair to switch on the voltage to our N channel. So our P channel switches, the gate voltage goes low, so the P channel switches on. The N channel gate voltage goes high, so it switches on as well. So they're switching on together. We create a dead short through the inductor, and then they switch off. Notice I don't have huge amounts of ringing on this. A little bit of ringing there, but so little. It's not funny. Do we need a snubber circuit for it? I doubt it. So let's go up to 14 volts. So we're at 7, 8, 9, 10, 11, 12, 13, 14. Again, no load. So, but look at our regulated voltage, 5.9. We're going to come down to the 7 volts. So it's 13, 12, 11, 10, 9, 8, 7, 6 is our switchover point. So 7, still the voltage regulation on the output is rather excellent. From 5.7, 5.8 to 5.9 volts, not bad at all. So we're talking about 10 millivolts of swing on our voltage regulator. Not bad at all. Remember, we don't have any load on this. So what I'm going to do, just for interest's sake, if we go back to 13, at 13 volts we are pulling 20 milliamps, which is roughly 0.26 watts. We'll go up to 14 because we said we wanted our circuit to go up to a battery voltage 14.7, so we'll go to 14.7. 6, 7. So I'm going to just do the maths quickly. We know on the output we have a 180 ohm resistor, so we're going to take our 5.95 volts here. 5.95 divided by the 180 ohm will give us our current, which is 33 milliamps. Square the current times 180 will give us our power. P equals I squared R. So it's 196 milliwatts. On this side we're putting 279 on our power supply on that side, so I'm just going to do the math for you. 196.681 divided by 0.279 times 100. Well, we're getting 70% efficiency as is, so not bad. I'm going to come down to our 14 and go back to whole step increments. 7 volt, 6 volt, we lose it, so 7 volts. I'm going to now put in our little 10 ohm load resistor so we can see what does it do to this waveform. Important, we've got 5.8 volts here. I expect that to drop. Let's put our load resistor in. Whoa, look at that. So our load, you can see our switching waveform going on. Let's just make it a bit bigger for you so you can actually get a better look at that. Let's bring in the time base. So what you can actually see, let's change our trigger. What you can see, our transistor is spending more time in the conductive state. So excellent. The circuit is sort of working like it should. Our voltage regulation has come down a bit. I'm not too worried about that. Let's step our power supply up. As a matter of fact, we are pulling 0.562, so our current sense resistor, if you remember, when we put that in, our current sense resistor up here, it's doing its job. It's limiting the circuit to half an amp. We are sitting at 7 volts, 8 volts, 5.31, 9 volts, 5.4, 5.3, 10 volts, 11 volts. Let's just change our 12 volts. I can hear the inductor starting to whine. It's not the best. Still 5.4, 13 volts, 14 volts. And notice how nicely our regulation is going on. If I do an efficiency calculation quickly, so we know we've got the 180 ohm in parallel with the 10 ohm. So I'm going to go 1 divided by 10 plus 1 divided by 180. The reciprocal of that gives me 9.474, which is our total load. So we're running at 5.5 roughly, 5.5. 5.5 divided 9.474 will give me my current of 580 milliamps. X squared times 9.474 is 3.193 amps. Watts. Sorry. Output power is 6.451. So we divide it by that times 100, and we are basically down to 40% or 49.49, so 50% efficiency. Does the circuit do what we want? Yes. Is it the best way to do it? No. I'm going to just turn our voltage down. Let's go to 6-7 volts, and let's do the same calculation. We'll put our load resistor in. Let's change our okay, so we've got 5.24 volts divided by 9.474, 553 milliamps. Square that times 9.474 of the resistance will give me 2.898 watts. We're actually putting 3.8 from the bench power supply, so divide that by it's 3.902. Come on, 3.902 times 100, and we're getting 74% efficiency. So at a low voltage we are doing okay, at the higher voltages not quite. Either way, our circuit is behaving like a buck boost, and we can say that it is regulating the voltage. Like I say, is this the ideal way to do it? Probably not. I wouldn't use this chip for buck boost. This chip is dedicated to either doing buck boost or inverting, one of the three together, or one of the three at a time, not two of them together. So we've, to all intents and purposes, made it a buck boost. I don't think it is the most efficient way of doing it. I will make the circuit available for you in the description below, and yeah, if you've got time to play, yeah, it's not bad at all. So we'll set up for the final shot, and we'll catch you then. Right, boys and girls, we reached the end of another episode. We've shown that it is possible to build a pseudo buck boost with the MC33063 IC switching regulator. Not the most efficient way of doing it, but as always, you should have fun with these things and experiment. I hope you learned something. As always, it was fun for me. Anyway, till the next time, take care, be safe, cheers.